Hi there, question number 6. The matrix P is given by P is equal to 1, minus 1, 1, 0, 2, 1, 0, 0, minus 1. State the eigenvalues of P for part A, and part B, use the characteristic equation of P to find P inverse. Also, the 3 by 3 matrix A has distinct non-zero eigenvalues A, half, 2, with corresponding eigenvectors 1, 0, 0, minus 1, 2, 0, 1, 1, minus 1, respectively. Find A inverse in terms of A. Now, the eigenvalues is very straightforward because this is a triangular matrix with 0, 0, 0 here. So 1, 2, and minus 1 are the eigenvalues. 1, 2, and negative 1. Now, to be able to find the characteristic equation of this matrix, what we use is this formula here. Matrix P minus lambda I is equal to 0. So we're going to be using the determinant of this matrix here. And if we were to do lambda I, we're going to get all of that because I is 1, 0, 0, 1. 1, 0, 0, 1, then 0, 0. So we multiply this by lambda, we get all of that. So therefore, I'm going to take P, which is this matrix, minus lambda I. And so here we are, then 1 minus lambda. Then we've got minus 1 minus 0, which is minus 1, and I've got 1, 0. 2 minus lambda is 2 minus lambda, and then 1 minus 0 is 1, and I also get 0, 0, minus 1 minus lambda is minus 1 minus lambda. Yes, now we have this equates to 0, and this is plus, minus, plus. So basically now I've got 1 minus lambda over here, so 1 minus lambda. Then the matrix is going to be equal to 2 minus lambda here, 1 minus 1 minus lambda, and then I've got 1, 0. And then minus becomes plus, and I've got 1 into, of course, 2 minus lambda, so this over here, no, this one is cross, this one is cross, I've got 0, 0, 1, 0, 0, 1, and then minus 1 minus lambda, and the determinant of this is basically 0. So then I've got plus, okay, 1 over here into the determinant of this matrix here, so 0, 0, and then 2 minus lambda, 0, and of course this turns to 0. So what I'm left with is now this 1 minus lambda into 2 minus lambda times minus 1 minus lambda, and all of that is equal to 0. Now if I were to multiply this whole matrix here, I'll end up with lambda cubed minus 2 lambda square minus lambda plus 2. And well, this is p to the cube minus 2 times p to the square minus then p plus 2. And of course, if I bracket this, multiply by the inverse of p on both sides, it ends up as p to the square minus 2p, and so that should then be minus p times this thing here is p to the power of 0, which is identity matrix, and then 2 times this is going to be equal to plus, okay, 2 times p inverse, and all of that is equal to 0. Rearranging this, we get 2p plus I minus p squared divided by 2. So on this side here, what I've done is I've just multiplied found out p square, and then of course 2p, and as well I need the identity matrix, which is here on this paper, right? So we're going to just take all that matrix here and substitute in here 2 times p. So the p inverse is going to be equal to half into 2p, which is what we've just found here, 2 minus 2, and then 2, 0, 4, 2, 0, 0, minus 2, that's my 2p, plus the I, so plus 1, 0, 0, 1, 0, 0, 1, 0, 0. Okay. And after substituting all those matrices, this is what we get. And of course, this leads to finally P inverse half times the result of that, which is here, and that's your inverse for matrix P using the characteristic equation. Okay, for part C, we were told that we have a 3 by 3 matrix A that has distinct non-zero eigenvalues A, half, and 2 with corresponding eigenvectors. All of these are eigenvectors, and we need to find inverse of A. Now, before we do that, we need to find the diagonal matrix, okay? But we can use the formula to find A inverse, which is basically A power n is equal to then the matrix of the eigenvectors times the diagonal matrix d to the power of n and times P inverse. Remember, we had P inverse in the beginning of the questions, all right? So the P inverse was actually 1 half 3 over 2, 0, half, half, and then we had 0, 0, negative 1. Now, the diagonal matrix is the matrix of the eigenvalues, and those are A, half, and then 2. But because we're looking for d to the power of negative half, why? Because here, A power n, d power n. So the power is negative 1, so all of that is going to be the inverse reciprocal of these. So this is going to become 1 over A, and then instead of half, we're going to get 2, and then here it's half. So we have 0, 0, 0, 0, 0, and 0. And the matrix P is the matrix of the eigenvectors. So matrix P is matrix of eigenvectors. All of those matrices, 1, 0, 0, minus 1, 2, 0, 1, 1, negative half. Negative 1. So to find A inverse, we just need to put those matrices over here. So A power n is A power negative 1. And we have our matrices P, the diagonal matrix, d power n, so this is P, d power n, and that matrix. So we're going to put all that matrix over here, and this is what we get. Now we're going to multiply those matrices. So I'm going to multiply those two matrices first, and after having done so, this is what I've got. Those two matrices are this one now. So now we're going to take this one, multiply by the other one. And finally, after performing these multiplications, this is what we get as a matrix for the inverse of A, using eigenvectors and eigenvalues. Take care.